Greetings, A-level chemists. This question is all about the ionic product of water, and we've got Kw and it's temperature dependent, and we've got two different temperatures, 25 degrees C, room temperature, and 40 degrees C. So using the data provided, we've got to determine the pH of pure water at 40 degrees C, and it's a 2 marker. Okay, we'll start with a bit of background about Kw. So first let's look at the auto-ionization of water. So we know that pure water doesn't really exist, and to a very small extent some water dissociates into H plus and OH minus ions. Now the forward reaction is endothermic. So we're breaking bonds in the water, and that's taking in heat, and we're generating a proton and hydroxide ions. Okay, so the reverse reaction, because we're bond forming, that is exothermic. So we can apply Le Chatelier's principle here to these questions. And don't forget to apply that if the question asks for it, okay? All that GCSE knowledge is good knowledge. So where do we go next? Well, what we can do, let's write the equilibrium constant for concentration for this process. So Kc for this would be equal to the concentration of the hydrogen ions multiplied by the concentration of the hydroxide ions, all over the concentration of water. Now, what can we assume here? That the dissociation is to such a small extent that the concentration of water remains constant. Okay, so the dissociation is absolutely tiny, so the assumption here is that the concentration of water doesn't change, and it's a fair assumption. So how does this resemble Kw? Because Kw is given as the concentration of protons multiplied by the concentration of hydroxide ions. So how do we go from Kc to Kw? Well, what we can do is we can multiply through in equation number 2 by the denominator term on the right hand side. So we can multiply through by the concentration of water. Just going to get rid of Kw for a second to make a bit more space. And if we do that, you will see that the concentration of water, that term cancels out. Okay, still doesn't look like Kw, but we're getting there, okay? Now remember that Kc would be a constant. Let's call it constant 1. We've said that the concentration of water effectively doesn't change, so this is a different constant, so constant 2 if you want to call it that. So one constant multiplied by another constant just makes a new constant, and this new constant is going to have the label Kw. So Kw is equal to the concentration of H plus ions multiplied by the concentration of hydroxide ions. And there you go. And remember that this is temperature dependent, okay? So if we increase the temperature, let's go to Le Chatelier's for just a second. So if we increase the temperature, the equilibrium shifts in the endothermic direction to counteract that increase in temperature. So it absorbs the heat. So it moves from left to right, making more H plus ions. So we're guessing here that if the concentration of H plus ions is increasing, well, the pH is going to be less than 7. But remember, it's still going to be neutral, because as the concentration of H plus ions increases, simultaneously the hydroxide ion concentration is increasing as well, okay? Because the relationship here in the chemical equation is 1 to 1. So for every H plus ion we get, we also get hydroxide ion. Just remember that. So it's going to be neutral, okay? But remember that pH is a direct measure of the hydrogen ion concentration, so it's going to be less than 7 if we increase the temperature. So let's see if this is true. We're going to use Kw, and then think about what we're trying to work out. Okay, so the question is asking me to calculate the pH of pure water at 40 degrees. And then I've got to remember that pH is a measure of the hydrogen ion concentration. So I'm trying to work out this term here, the H plus term. But it looks complicated because I'm given Kw, but I don't know the hydroxide ion concentration, do I? But I do, because what we said earlier is that when we get one proton, we also get one hydroxide ion. So at equilibrium, the H plus concentration equals the hydroxide ion concentration. So what we can do in the next step is say, if these guys are equal, this reduces to H plus squared, and it simplifies the problem. Because I know Kw, and to get rid of that pesky squared term, I just take square roots of both sides. So the square root of Kw equals H plus. So where do we go from there? Kw is given to me. It's in the question, okay? So this is the square root of 2.92 times 10 to the minus 14, and all of that equals H plus. So let's process that on our calculator. So square root of 2.92 times 10 to the minus 14. Okay, looks about right. So we get something around 1.7088 times 10 to the minus 7 mole per decimeter cubed. Okay, then what I need to do is use the pH equation and substitute that number in. So the pH equals the negative log of the hydrogen ion concentration, which we just worked out. So let's do this. So negative log of the answer, and there you go. We get a value of 6.77. And that is a pH, and it's gone in the direction that we expected it to go to. Still neutral, so the neutral point of water is just shifted. But shifted because the H plus concentration is equal to the hydroxide ion concentration. Okay, hope that was helpful. We'll leave it there. Thanks for watching. Ta-ta.